Ladies and gentlemen, welcome to our webinar titled Simulation to Reality Enhancing Drone Inspections with AI-Driven Analysis. I am Tanushka, and on the behalf of Walking Tree Technologies, it is a pleasure to have you all today. Yeah, we have an exciting session ahead exploring the convergence of simulation technology and artificial intelligence in revolutionizing drone inspections. Before we delve into the details, let's extend a warm welcome to those who are still joining us. For those who are unfamiliar with Walking Tree Technologies, we are pioneers in driving technological innovation, specializing in implementing state-of-the-art solutions, particularly in emerging technologies like AI and Unreal Engine. Today's webinar focuses on the convergence of these cutting-edge technologies in revolutionizing drone inspections. At the conclusion of the webinar, we will reserve some time to address your questions and insights. Please feel free to submit your queries in the Q&A box during the session. Let's make this an interactive and enriching discussion. So without further delay, let me introduce our esteemed speakers for today's session. Beginning our agenda, we are privileged to have Scott Seabold, our Chief Technology Officer, lead the way in exploring dynamic intersection of simulation technology and AI-driven analysis in revolutionizing drone inspections. With a distinguished career spanning decades in technological innovation and strategic leadership, Scott's built a wealth of experience and forward-thinking vision to our webinar. Continuing our agenda, we are privileged to have Dikshit Nahar, our ML Tech lead, join us as a key architect in our journey from simulation to reality in enhancing drone inspections with AI-driven analysis. With over a decade experience in developing and leading cutting-edge systems in computer vision, NLP, and generative AI, Dikshit brings a wealth of expertise to our webinar. Last but definitely not the least, we are honored to introduce Najmu Saqib Shora, our technical lead, as a guiding force in our exploration. With over 7 years of expertise in game tech, Najmu is proficient in popular game engines. His broad experience equips him with a deep understanding of how simulation technologies like Unreal Engine can be leveraged to enhance real-world applications, including drone inspections. His insights into the mission planning and real-world deployment of drone technology will provide invaluable guidance to our audience, offering practical strategies for implementing AI-driven analysis and optimizing inspection. Our webinar aims to provide participants a comprehensive understanding of how simulation technology and AI-driven analysis are reshaping drone inspections. Through real-world examples and practical demonstrations, our speakers will illustrate a transformative potential of these technologies in enhancing efficiency and accuracy as well as safety in inspection processes. Now, as our distinguished speakers take the virtual stage, let's embark on this journey together and explore the exciting possibilities that lie at the intersection of simulation and reality in drone inspections.
Yeah, so those photographs are then used to construct a 3D model, and that 3D model it can be then brought inside the engine. So you can add geospecificity to it. For example, what we are using is cesium, and this is the approach that we basically followed. So we produced a photogrammetry asset, and then we used cesium for adding georeferencing, and that basically added the geospecificity. And then after that, each basically we could represent each point in space with a geographic location or a geodetic location, and that is the approach that we follow. But another approach is that you can actually build the site in the engine itself. So not using photogrammetry like the traditional kind of techniques. The advantage to this is that you will get more fidelity graphics wise, which you won't get with photogrammetry, because photogrammetry still has some kind of visual errors, which we can be avoided if you go with the synthetic approach. Okay, but you can also combine the approach, so that's also a possibility. But then, yeah, you also need to think about how you'll be adding the georeferencing. So Unreal does have a georeferencing system. We're using the cesium georeferencing, but Unreal also has a georeferencing plugin that you can use to add that. So once you have that, you have your static digital twin. It has georeferencing. Now you have that. Now, what is the next step? So what you can do at this point is that you can conduct the mission inside the simulation, and you can have the drone. You can control the drone inside the simulation. You can fly the drone around, and then you can go to points of interest. You can go there, and then you can basically capture waypoints at these points of interest. And basically, these waypoints, they they can contain multiple pieces of information. For example, what we are capturing is position. We're capturing the yaw. We're also capturing some camera information. For example, FOV, gimbal angles. That's the camera angle that at that location, at that point, basically. And yeah, so now you have this data. It's inside the waypoint, and then at that point, you can basically take this data and then save it to a data format like JSON, and then you can go from there. I'm just gonna do a small demo here, and we'll be using a public GIS data of a oil company site, and we'll be using AirGen and Unreal Engine. AirGen is actually for the drone dynamics, and Unreal Engine is for the rendering. And Unreal Engine and AirGen kind of work together, so we have to use both of them. And the site that I was talking about, the GIS data, it's actually from Google Earth. You can see that it does not look like very high resolution because it's public data, and yeah, it's from Google, but I'm not allowed to show the actual site that we have, so we'll have to go with this for the demo. So yeah, with that said, I'm just gonna play in the Unreal editor, and I hope you can see. Is the window visible? What? Oh,
it is.
all right. Just give me a second. All right. Okay, so let me just set up the thing. All right. Have to. Yeah. Okay, so right now I have the drone. I'm able to control the drone, but we'll add better control using PyAirGen. So PyAirGen is the Python interface for AirGen, and I'm just gonna run a script that we have written for mission control. And now I have run it, and now I'm able to control the drone using my Xbox controller. And you can also use an actual drone controller. So that is also a possibility. You just have to capture the inputs from there and then call the PyAirGen API. Right now, with this script, we are capturing inputs from the Xbox controller and then calling the API. And yeah, so now you can see that I'm able to move the drone around. I'm able to apply thrust. I'm able to change the yaw. I can pitch forward. You can see that. I can pitch back. All right, so I can basically move the drone around. And this is position control, which means that the altitude will be maintained unless I change it. And you can also control the camera. You can see that I'm controlling the camera. I'm using my triggers right now, the triggers on the Xbox controller. And this is the actual information. This will be, whatever I have here will be captured as part of the waypoint capture. So the way the mission is conducted is that we start with a ground point. Okay, so we start the ground location. This is the home, what we call the home. So we can choose, let's say, a point here. And then I can basically start here. So this is, yeah, so I've created a home, basically a home point. And then I can move to any point. Let's say I want to inspect some place over here. And then what I can do is I can, choose the angle, and then I can create a waypoint. I can also undo if I want, but yeah, I'm just going to create again. And then basically I can go somewhere else, and then I can adjust my drone angle. And again, like I said, the quality of the visuals depends entirely upon you. And that's not the point of this webinar, but basically, there's multiple ways of creating the digital twin, like we said. And as long as the digital twin is, it kind of is representative of your actual site, yeah, you should be able to kind of conduct missions in the sim and then replicate those missions in the real world. And that's the whole point. So it's going to capture one more waypoint here. And then, yeah, for now, I'm just going to call it a day. And then I'm just going to basically hit, I'm going to press a button on my controller to kind of end the mission. So at this point, we actually have the waypoint data captured. So we just captured waypoint data. If I wanted, I could basically, we have added one more script which allows you to play back the mission in the sim. This isn't important, obviously, for the actual kind of the use case, but it kind of helps us to, just to iteratively see whether whether the path that we have created is what we want, or if we want to make some changes there. Basically, but as you can see, like the way drone basically conducted the playback is how it will conduct it in the real world, which is basically it will launch and it will go to the waypoints. So it will go from one waypoint to another, and then during that, it will basically use the data to rotate. So it will have, because it has your information, right? So it will use that to kind of basically rotate towards that location. And then finally, what it will do is that it will go to the return to height, sorry, the return to home altitude, and then it will basically, after that, it will just land. So um, that is the flow, and that we cannot show, unfortunately, the actual footage of the actual drone flight, but basically that is how it will be. Okay, and we'll talk about that a little more. So I was just showing the playback inside the sim. So you can see that at the end it's kind of going back and then it's landing at the home, right? So I'm gonna close this now. Just give me a second. And let's go back here. Okay, so when I basically ended the mission, I captured waypoint data, which looks something similar to this. And basically, there is a couple of things to note here. First off, you might notice that this number here is I mean, in terms of accuracy, it's there's a lot of digits here, right, on the decimal side. And this is possible because of the large world coordinate support in Unreal Engine 5. So earlier, what used to be the case is that there used to be floating point errors, and we had to do a bunch of workarounds to get around this. But now we don't have to do any of that. The support is inbuilt, and yeah, the captured lat long altitude is, I mean, they are very accurate. So because, I mean, for those who know, if we just vary just one of these digits, that actually results in a lot of change in the real world. Okay. So yeah, so that's why this is really important. So the support for large world coordinates. And yeah, so you can see, like, we have captured lat long altitude, we have captured the roll pitch-yaw, we also have quaternions, which I'm not showing here. We also have information from the camera at that point. For instance, the rotation. If you have any kind of offset, we can also have that. But FOV as well. And this is in JSON format, right? So we are using the same JSON for the playback. Now, for the actual real world drone, we need to convert to an applicable format. The drone model that we're using is DJI. DJI Emittries 300 RTK, I believe that's the model. So what we had to do was that we had to convert it into a KMZ format. And so we wrote another script for that and then converted from JSON to KMZ. And while it was converting, we could, so one nice thing about KMZ is that you can actually add actions at these waypoints. So we can say that, okay, at this waypoint, perform an action of photo capture. Okay, so the drone will basically, when it actually goes to that waypoint, flies to there, it will capture a photo before moving to another waypoint. So basically, yeah, so we did the flight in the actual, we did the flight in the sim. We captured waypoints. we did playback just to test, and we can iterate over this. And then once we're happy with that, we can take the JSON, convert to KMZ, and then basically use that KMZ in the real world drone. And then the real world drone will then perform obviously flight in the real world, and then it will go to the same points that it did in the digital twin version. It will do in the real world version, and then it will capture imagery. So this can be video or static images, and you can do inspection and analysis on that. And so there's a couple parts to this. One is the autonomous navigation, because you're not using a pilot here. You're just letting the drone use the data and then do the flight, which is really beneficial. And then there's other aspect to this, which is the inspection and analysis. And at this point, I'm just gonna hand it over to Dixit to talk about that part. Yeah. Dixit, over to you.
Yes. Hi, Najam. Yeah, thanks, Najam. So let me take this over. Okay, all right. So when it comes to inspections using drones, or basically when we want to put ML models into production, largely we are looking at two kinds of deployments. One is on-device deployment, and one is not on-device, which is called an offline deployment. So on-device means that the AI models and all the other models are running on the device. Here, the device is the drone, and uh, how it is beneficial, it is of course very beneficial. You don't need a separate VM. Your data is going to be in the drone only, and it is very cost beneficial, and a lot of the tasks can be done through models running directly on the device. And these days, many drones are coming up with a lot of computing power, in which we can run AI models directly on the drones for a lot of the tasks. The second way of deployment is that, okay, let's say we have sophisticated models which we want to make use of. In that case, we want to shift the intelligence on a virtual machine, which will still be on the premise, which can be on the cloud or on the premise. And the intelligence part will be on the virtual machine, and the navigation part is of course going to be with the drone. But there is going to be a constant communication between the two. So this is also on. So the reason I say online is because the intelligence part, the intelligence, that the insights that we want to derive from inspection, this is happening while the drone is in flight. So the online inspection also can be done where the pilot or someone who is looking at the images that has been shared by the drone, and perform basically inspection on the fly still, and navigate the drone according to the waypoints that we want to set, according to where we want the drone to fly around the oil pipeline, or around any kind of environment. So, and the last piece of deployment here is going to be that the drone is only going to capture the images from the waypoints. So we have set the waypoints according to how we want to do the inspection. The drone is going to take the flight and go to the respective waypoints, go to the respective positions, and capture the images, and store it, and store it for offline inspection. So there's another way to do the inspection. Why we set the waypoints is because oil pipelines or these kind of environments are very static in nature. So we set the waypoints so that whatever analysis that we want to do in our premises, we can actually control that by putting waypoints. So all of this are quite different. Autonomous navigation many of the tasks are actually being done through autonomous navigation. Here, a definite cost benefit is there, that you don't need someone to be looking at what's going on with the drone, and which which will bring a lot of productivity increase and bring down the cost. Now, talking about autonomous navigation, how do we actually achieve that? So now, to bring on autonomous navigation of the drones, safety, obstacle avoidance, path planning, these are the things that we need to consider. And when it comes to safety, we want to identify what's happening in front of the camera. So in front of the drone. So drones are equipped generally for AI. Drones are equipped with two cameras. One is kind of in the front, which can actually rotate independent of the drone by raw pitch yaw angles, and there's one camera at the bottom generally. So which is going to help. So drone can look at kind of two. It is equipped with two cameras along with other sensors, which are IMU, barometer, and these kind of sensors. So there are infrared sensors also. So now we have the cameras, but of course we don't know where the drone is now, or there are obstacles which can be moving in the environment, even if we are going to static waypoints. But we need to ensure that the drone is not going to bump into something, or some moving object is not going to come in front of it, or if there is a moving object, we need to identify that. Now, depth maps models are one of the which will help us to understand, which will help the drone to understand what's in front of it, how many objects are there. So relative depth estimation and metric depth estimation is one of the two categories, other two categories in the depth maps model. Relative depth is going to just tell the drone which object is nearer and which object is the furthest. But actually, what we need is in some of the use cases, the relative depth estimation is going to be sufficient, but mostly we would need metric depth estimation. That means we want to identify how far the object is from the drone. So that is what the metric depth estimation is. And if you talk about what are the models to get this, depth anything is one of those models which will provide you relative depth estimation and metric depth estimation. Midas is going to provide you relative depth estimation. Zoe depth also is going to provide you with relative and metric depth estimation. These are kind of the state-of-the-art algorithms which is present out there. There are so many different versions based on the size. In the depth anything, also in other of these models. There are several other models, but I think these attract the most attention. And so yeah, so this is one of the experiments that we done to briefly understand what kind of output that we get by applying models. So on the left side, this is the drone front camera. This is on the AirGen simulation platform. This is in Unreal Engine, and this is how the drone sees. On the left side, this is what the RGB image from the camera that we get. This is a very small image, 256 by 256 resolution. And just on a small image of this kind, this is the output that we are getting from the depth models. So this is the depth anything output for metric depth. And this is the output for Zoe depth. This is the AirGen platform provides the ground truth. So basically what this gives is like a 256 by 256 map of where these objects are. So here the values are basically in meters. So it will just say that, okay, the darker pixels are kind of close to the camera, which will have lower values. It's not ranging from 0 to 255. This is a metric map, and every pixel is going to tell you how far that object is from the camera in metric terms, which is meters. And depth anything is also doing that. Zoe depth is also doing here that. So this will, we can see here, that the metric depth is providing us quite a good information about what kind of objects are present and how far they are. So if you see the fourth dimension here in the depth and the Zoe depth, they'll provide the metric information. And So this really gives one piece of information, how far the object is. Of course, we cannot rely on one model to understand how far the object is. Um, and this is just another image to basically help us understand. Now, the ground truth here is very important for us to understand which one is the better model of the for metric depth estimation. And we established that depth anything model, this particular model, is actually better when it comes to identifying the different objects which is present and the relative metric depth that we get from the image is something that is better at least for this particular environment. So it is something of an interesting. It's an open source model which we can all these models are open source models. So this is the beauty of the Edge and platform, which provides ground truths so that we understand, we can build which model is going to be better for our use cases, and accordingly we can actually work on figuring out how to build our solution. Now, metric depth itself is not going to be enough to ensure safety, or so we need to do more, and that is where optical flow network and optical expansion comes into the picture. What optical flow is basically from consecutive images, how the pixel moves when the drone is moving. The other objects seem to feel that the other objects are also moving past it. And this is what the idea behind the optical flow estimation. What it will help us is to understand which are the moving objects in front of the drone, which objects are moving, which objects are static. We'll also understand what is the velocity and what is the direction of the moving objects which is present in front of the camera. And so in that way, this helps us understand that it helps us understand what is the point of collision that is going to happen, and what is my own trajectory that I should take to understand how I go about without colliding into anything. But the optical flow itself is not sufficient, and that's where optical expansion comes. This is like a 3D expansion of the optical flow, which is a 2D output. It is 3D expansion, and what it helps to understand is the depth. Basically, it estimates helps us understand that how far the moving object is from the camera. And again, this is like a very useful phenomenon to know that how far the object is. This helps to so that we are not relying on one particular metric or one particular model. We are not even relying on whatever the sensors are present in the drone. We have to rely on multiple models to understand where the drone is going to be in its entire flight. So that's where optical expansion comes. I put links here to the authors who have, again, this is an open source model. This is something that we can really check out. We implemented this. This is just an understanding of how it looks like. What it shows is that on the left side, this is like the ground truth. This is the video, and on the right side we have the optical flow, and what we have on the right side is the optical expansion output. Now, how that helps is it gives a quantifiable way to understand where the objects are, how far they are, and how fast they are moving towards us. So this particular demonstration just says that if the objects are very close to the camera, or getting very close to the camera, the the object is going to look like it is going far from the focal point of the camera, and that helps us to understand how far a particular object is from the camera, and what are the static and what are the not static uh, objects. So yeah, with that, let us come to inspections. So inspections are, of course, going to be so many of different types. In the case of oil inspection, these are one of the few inspections that we want to do. We want to identify cracks, we want to identify damages, corrosions, not just of the pipeline, but really about the entire facility. And any kind of inspection related insight that we want to generate, we are really interested in to find out. And that is supposed to be derived from the images which has been captured by the waypoints. So what are the models that we can use to perform inspection? Yeah, so when it comes to on-device analytics, what we need is the models which are very lightweight and which are accurate. And YOLO series, as you guys would know, is really the best of the art, arguably the best of the art, state of the art models when it comes to precision, when it comes to basically a balance between accuracy and speed. And when it comes to on-device analytics, preferably, personally, I feel the YOLO series are really one of the best models that we can bring directly onto the camera. Like, for example, YOLO V8, the object detection model, which is the nano version of it, like YOLO V8N, is only 6 MB. So the model is only 6 MB, which really can run real time, providing us a lot of FPS, and which can run on device, basically on any kind of device. 6 MB is really and it provides a kind of accuracy which is productionizable. So I've seen most of the models which are put into production has the scalability factor and the cost factor. And when it comes to talking about those kind of questions, the answer is the YOLO series of models. Uh, Talking about other models, YOLO models, it's a CNN model. It's a convolutional neural network architecture, and what it needs is that it needs training to be done on the task that we want it to perform. It's an object detection model. Now, to perform the other models in the section is again, I'm only putting those models which have done quite well for our work. The grounding Dino is a transformer architecture model, and OWL V2 open world localization vision transformer model. This is the another transformer based architecture. These are zero shot detectors. YOLO is not a zero shot detector. That means it needs to learn which object it needs to be, which we want to use it for identification, for detection. But we don't have to provide any training to grounding Dino or OWL V2 kind of models. We just have to basically state what we want these models to identify. Of course, YOLO V8 is very fast compared to grounding Dino. Grounding Dino is in these three models. Grounding Dino is the second pass, and OWL is slower than the other three. When we want to do offline analysis, we can do a lot more. Of course, we can use grounding Dino with segment anything model to identify the areas of where the damage is. And similarly, with OWL V2 plus SAM, we can also use YOLO plus SAM to exactly identify, to segment basically the areas of damage, and that can help us to provide a precise report of the extent of damage that is there and where all damage are. And these two are the multimodal models, which I'm going to talk about how we can make use of this. Now, coming back to YOLO, most of the algorithms which are put into production are actually YOLO models. I mean, this is my personal preference also for most of the work. But what it needs is a training data. Now, that's where the power of digital twin with Unreal really comes in, is providing us training data, providing us the synthetic data that we want. Now, for example, if I wanted to inspect for fire in a forest like this, the fire is actually quite far from the drone, and so I want to generate so many images, and I want to train my YOLO model, let's say, uh, with the data like this, so that the YOLO model can actually detect fire from a distance. So this is where these environments, when we create these digital twins in Unreal Engine, that's where it becomes very useful for us. Uh, we created a data set of fire and smoke for fire and smoke detection. And this is how the data set looks like. Uh, and what we have done is that we have applied the OWL V2 model, which performs best, uh, to basically annotate this. So we don't have to annotate for training our YOLO models. So this is where really we can actually create, when we have a digital twin, we can actually create any kind of training data. Like we have gone close to the fire, we have gone around fire, and we have taken images, around 3,000 images of so many different angles. Uh, when we have moved around a drone, this will help us capture the synthetic data that we want, and we'll train our model so that at least in our premises, the YOLO model will perform the best, and that is the best thing that we want, really. So yeah. Now, when it comes to using YOLO V8 model, or any kind of model, any kind of a CNN-based model, convolutional neural network model, we first go ahead and annotate these. When it comes to segmentation, we are actually creating polygons using the annotation tools to annotate the region. Like this is like the polygon that I'll create in an annotation tool around the damage that I want the YOLO V8 model to detect. V8I is the instant segmentation model. These are the annotation tools which are open source: Label Me, MakeSense.ai, and Label IMG, which are really good for the use case. And we have built the YOLO model. We have trained a YOLO model to identify cracks and damages, and we see that it really performs well. This is not even the best of the YOLO, the biggest size model. This is the YOLO V8 medium size model, which is a 50 MB, 50 MB model. It still performs really great to figure out the damages, the segmented part of it, the cracks as well, giving us a decent confidence as well. So again, like when it comes to production, putting things in production, YOLO V8 and YOLO series is for personally have really been very helpful. So this is something, a combination of grounding Dino plus SAM is used to annotate, kind of autonomously annotate the data that we require to train models. And this is how so we perform detection using grounding Dino, and on the detected area, we perform segmentation on top of it. So this is like the output from the grounding Dino for corrosion. And this is what we get. We get the entire pipe, which is corroded. So this is this is used to identify the corroded area. Yes, this can also become a training data set, an annotated training data set. That is also where grounding Dino plus SAM are used for segmentation related problems. Now, OWL V2, this is one of the relatively newer models, you can say. Uh, Again, the idea is similar. It is a transformer-based architecture, which will take two inputs. One is the image itself, and one is what you want to basically detect. So uh, I'll get into it. So these are all zero-shot detection models, and I'm really impressed by the accuracy that OWL V2. It is quite robust. So if we know what we can provide here is uh, basically we can provide a caption of exactly what we are looking for here, or we can provide directly the object that we are looking for. This is the same with grounding Dino as well. We can provide the caption like a sentence, what we are looking for exactly, and how we want to map it to a particular class. And we can provide a sentence. We can add as many as we want, and create a class list for detection. What we have observed in our analysis is that OWL v2 performs quite better than grounding Dino for an object detection task. It is slower, so it is expected kind of that, okay, it is going to perform better. But as you can see on the left side, OWL v2 correctly identifies the fire, and on the right side, it's like a false detection that was provided by grounding Dino model. When you apply the same image for OWL v2, it did not give the false detection. So what we have observed is that OWL v2 is really a very robust model, which can identify, which can detect a lot many objects, and we can really control what we want it to detect by providing the caption for it. Okay, now coming to the blip. This is a multimodal model, and why we need this kind of model is that now it's really not just detecting objects these days. I mean, we need to actually have a proper understanding from the images, and that's where these multimodal models come into the picture. Blip2 is one of those which has also gained a lot of popularity. It is used for image captioning, but it can also be used for a task like this, where we can provide a prompt like this. And it is really understanding the prompt, and it's providing the kind of the output. So what it's saying is that for this image, the urgency to repair is 3 out of 5, which is a great answer. It's like not a very big model. It's one of the faster running model. So it can provide description of the image. Like here also, it's a good pipeline. It is mentioning, it is able to provide the pipeline condition to be good. The good thing about that is that it is really following the instruction as well. So that is also a nice thing, that we can get it to output what we want. Here, if we are just asking it to describe the image, like look, I'm quite amazed by the way it is providing the description. So it is really able to say that the pipe is very rusted and needs to be replaced. It's like an amazing output that we are getting for multimodal image models like this, which is really helpful for inspection related tasks. And here we don't even have to provide, we just have to say that, check for inspection. And it is going to basically help us to identify all kinds of problems. So we don't have to really tell it to do this and do that. It will figure out, I mean, it is able to describe the image according to the context that we have set. And in this way, we can have a detailed understanding of what's going on in our environment. And this is another model, which is, we can say it is kind of state-of-the-art open source model. I really like it. This like, let's look at the result. This is the prompt that we have given. We have asked it to rate the urgency of repair, if there is, and this is the output that is given. And if we read through it, given the severity of the corrosion, I would rate the urgency of repair as 4. Because the materials, it is at risk of further deterioration, which could lead to leaks, structural failure, and other safety hazards. It's important to address this issue promptly to prevent any potential accidents or damage to the system. This is like amazing insight that has been gotten from an image like this. This is basically, in a way, it is a human level intelligence that has been really gathered and captured, which provides really a lot of what we want from models like this. This is another image that we provided. And the best thing is that here in the previous image, what was going on is that there was issue with the pipeline. It was able to identify that this is the object of interest. And here, when we provided the image where some sort of fire is going on, when we are asking it to describe this image for inspection, uh, it is able to identify that the emergency response is going on with firefighters attending to a fire. uh, like you see, the visibility of the firefighters are really not so good. Still, it is able to identify uh, everything basically that I can think of that I want from an image like this. Is able to identify visible smoke, indicating active fire incident. Fighters are present, wearing protective gear, are connected to hoses. Hoses are laid out on the ground. There's a ladder. Building suggesting firefighters may be accessing. So it's also able to identify the action here. Uh, 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 Maybe accessing the upper levels of the structure. The building appears to be a single story. So this is the beauty of these kind of models. Again, this is open source. This is something that which we can use for basically, along with a small language model, we can actually use the small language model as the kind of the orchestrator to understand this insight that we have gotten and provide a quantifiable report of for the inspection. So that is where these models really have a lot of potential. Uh, we can build an orchestrator around all these models, along with the computer vision models, how to best make use of it while the inspection is going on. So uh, uh, this field is actually quite exciting. The results that we have seen while working with these models uh, is something that has been really making us believe that autonomous inspection, highly detailed and a thorough analysis is really right at the corner. With this, I would conclude, and it is up to Tanishka.
Yeah. So we have received a few questions in the Q&A box. First of all, Janie wants to know, how does the integration of AI technologies, specifically computer vision and machine learning models like MIDAS and ZODEP, enhance the accuracy and efficiency of drone-based inspection systems?
Yes. So Midas and Zoe depth, these provide us metric depth estimation and relative depth estimation. These are useful for the drone for safe navigation, and that's where it is very effective because even if we are doing even if we are doing even if a pilot is actually running the drone, it is always very useful that these models are running on the drone for its own safety and for its own understanding of what's happening in its environment. So that is where these models are critical. Metric depth estimation from Zoe depth or depth anything model, these are for safety and not really for generating insights, but these are really responsible for safe navigation of the drones. It can take fail-safe measures. We can attach like fail-safe measures when we see from the metric depth that some objects are getting very close, uh, and that will actually notify the user. Um, and it is going to take the action that is required for its own safety. So that's where these models are very useful.
Thank you, Dikshit, for answering the question. So the next question is from Michael. He wants to know, he has just dropped in a text. Please tell, how do current regulatory frameworks impact the deployment of AI-driven drone inspections, and what are the potential legal or ethical concerns?
Yeah, I'm gonna let Scott take that about legal and ethics. Uh, Scott, you're muted.
No, Scott, you're not audible to us.
Okay, how about now, guys?
Yeah,
Yeah, audible
perfect.
now.
All right. So kind of a, a couple things on this one. That the question is kind of a couple directions, right? And specifically, when it comes to AI-driven drone inspections. And so one thing, of course, just in general with the drone, it's got to meet airspace regulations, right? So that first and foremost doesn't really change just with the fact that it's AI-driven, of course. So that's first of all. So all the laws that still and regulations that are in place for drones are still in place in terms of, FAA regulations here in the US, or probably, I believe it's called EASA in Europe, I think it is. So any of those laws still apply in general, just for registered drones, registering drones, getting licenses, those kind of things. Those still apply. Now, when it comes to AI, of course, then you've got to deal with things like, what's the ethical use of it? What's the security measures you've taken, and any kind of consent and those kind of things that have been given, and trust in terms of AI and the airspace it's flying in. And I think the other thing is just dealing with the data concerns and everything, kind of related to the question we had before. You still got the data privacy laws and those kind of things, and even some more, even deeper than like, DPI type things. You've got location type things that come into play as well, right? But in terms of just regulatory, regulatory agencies and frameworks that are in place, I think some of those are still, in my view anyway, are still kind of, being worked out, just like ethical AI is being worked out. But I would say, all in all, I would say you've still got those same things for the drones. And then just in general, in terms of AI, just the ethical use of AI, right? I mean, when you're flying over an airspace and you're taking, you're taking photos and videos, you have to have the rights to be able to do that still, right? And I think any of those things still apply. I think in general, probably use of AI in general and the ethical use of AI. Of course, if we look in the U.S. and how those things are kind of being debated within the U.S., I think some of those are still, in terms of regulatory, are still kind of being decided. So I don't know that I know specifically, where those rules lie. I think too, industry wise, if you're talking about pipelines and those kind of things, I mean, I think there's still some issues, not just with the AI, but flying drones over those. So hopefully before you take off in this drone and using AI or just doing it manually, you've got the rights to do that kind of thing. So, and I think too, with AI and kind of going back to the data privacy and the security of it all, right, too. I think you've still got to take some pretty good measures there to make sure things are encrypted. Any kind of communication that's going on between the drone and any kind of server, right? There's some things that need to be in place in terms of encryption and those type activities. Of course, data storage, kind of the same thing with data in transit, stored data in transit needs to get encrypted in these cases, because most of the time when you've got these drones flying in areas, it's probably some data out there that's fairly proprietary to the company that's flying the drone or doing the inspections, right? So, or maybe a company's been contracted to do that, right? And that company is going to have to probably adhere to some regulations in terms of what the actual company says that they can do with that data. And then that kind of translates over to the data security aspects that are just general data in flight and at rest. So I don't know that I have honestly, Michael, I don't know that I have a specific answer in terms of the regulatory framework yet. I mean, from what I've seen, some of those things are still being written. But definitely, I'll tell you what I'll do with that. I'll post what I can find. I'll post something out on LinkedIn on that in response to the webinar. So I'll follow up post on that one. How about that?
Great, Scott. So next question is from Lyora. The question is, do you have GitHub repo example with the code?
Yeah, so first off, from the simulation point of side of things, the Airgen plugin is closed source, so if you have to work using that, you have to reach out to our partner, Scale Foundations. You can also reach out to us. And yeah, from the AI side of things, Dikshit, you can add.
Yes. So I think if you're sending the slides, most of what I've gone through, I put in the links which will help, which will actually which are about the GitHub links only. So if you're sharing the slides, I think that will generally help. What we have done for our clients, of course, we can share that, but now most of what we have shown for the AI side. I've discussed all open source models. So the implementation part is also provided in the GitHub links, which I've shared throughout the slides.
Yeah. So next question is from Caroline. The question is, what role do synthetic data sets play in training AI models for drone inspections, and how do these data sets compare to real world data in terms of model performance and generalization?
Yes, let me take this question. So this is like a very, very good question because uh, obviously synthetic data plays a huge amount of role when it comes to putting models into production because um, clients generally don't provide data set or access to their premises really, and we have to actually work without that kind of data that is coming directly from the client. Even if the client provides that access, it becomes very difficult to gather the kind of data set that we want from those cameras. Now that's where the synthetic data, the environment that we create in Unreal Engine, that's where it really helps. Now, coming to the quality of how good the environment is, we actually did this like when we uploaded those images that we captured from these environments, from the digital twins that we applied multimodal models onto it. You know, the state of the art. It is even those models are not able to identify if it is actually real or not. So that actually shows the quality of how simulated data set is actually quite real. You know, the kind of fire images that we have captured or the images that we have captured, for most of those images, the multimodal models are not able to actually say that this is coming from a simulated environment. But that actually shows how real these images look like, and it definitely helps because when we are training AI models, uh, what we are learning, what AI models are learning is the shape and the color and those kind of things. So, which is of course going to be present in the simulated environment as well. It should be actually the features that we that is needed for training models. These are already present in the simulated environment. Those images that we capture from there. So the features are still identical because the look and the look like the colors or the shapes, the edges, the corners, these kind of are not going to change. They are very true in the Unreal space as well in the simulated environment. So of course, these kind of data set is going to be very useful to train the AI model. So how good these images look like, I think even Najam can point out, how real the images coming from Unreal is to the real world.
Thank you, Dikshit, for this detailed explanation. So the next question is, can you please tell what are the cybersecurity measures in place to protect the data collected during drone inspections? especially when dealing with sensitive or proprietary information?
Yeah, I think Scott kind of touched on this before. So basically, I mean, if a mission is being conducted, ideally, the company will either own the drone as well, or they'll be contracting someone else who will have to follow certain guidelines. But yeah, I guess Scott, you want to add some more stuff here?
Yeah, no, I think it kind of relates to what I talked about earlier. I mean, those, there's several factors in there, right? You've got the communication, you got the data storage, data at rest, that whole thing comes into play. So it's all got to be encrypted when you're storing it, either if it's on device, if it's in transit, being transmitted, through whatever type signal it's being transmitted on, right? Or if you're just taking it and downloading it later on after you gather it, however that data gets gathered, right? If it's over air, it's got to be encrypted. If it's being stored on some media and then pulled out, of course, it's got to be encrypted at storage. So those same kind of things apply. And it's essentially, when the two areas, right, when you're going Unreal and moving that over to the drone, right, you've either got a couple different formats of files that you're pulling over into the drone. And basically, when you're taking that media, and Najim, how is that normally transmitted from the DJI? Is that normally transmitted over over Wi-Fi? Is it or is it just the storage media on the device?
Yeah, I mean, the one that we used for the actual project that we did, it was stored on the drone, so on a storage device, and then they extracted it once the drone landed. Yeah.
Okay, got you. So it wasn't really transmitting anything per se. It was on a storage media. So yeah. So basically, you're going to have to encrypt that data, just like you would any other data, storage, storage at rest type data, right? So you're going to have to encrypt it in the data store, whether it's the file system there, or if you're storing it in, from Unreal and you're pushing the JSON to some database or something, right? It's got to be encrypted there as well. So I'd say just normal encryption rules would pretty much apply here. And then, of course, like Najim said, I think too, is it really depends on the industry, and there's some more very specific guidelines depending on what you're doing. And that's a lot of times determined if we were doing something, and I can't really fathom what at this point in terms of like a medical use case or something. But there's certainly, I would say in this case, the big thing is the waypoint type data, and the drone instructions and what you're doing with those kind of things are very important. But they're going to be kind of industry specific, I believe. And then just the general basic cybersecurity practices that we go through as well.
Thank you, Scott, for answering the question. So that's it. We have answered all the questions. I would like to thank our speakers for sharing their expertise, and a sincere gratitude to each one of you for being a part of this webinar. We hope you found today's session insightful and inspiring. We look forward to welcoming you to our next webinar. Until then, stay tuned for the updates. Thank you, everybody.